You got it.
All right, thanks, Renan. Thanks for inviting me to give a talk on this topic. My goal here is to think about landscapes like you see in this title picture slide of Eastern Taiwan. This is in Eastern Taiwan, but thinking about the individual sort of weather events that lead to things like landslides and debris flows that send sediment tumbling down river systems, and how the implications of those individual events can leave a legacy and impact the evolution of these landscapes over longer timescales. So I had a whole introduction planned, given that this was going to be the first talk of CSDMS, talking about how I always love coming to this meeting because it's about, you can see models on different timescales from seconds, to thousands of year type time steps in our numerical models. And my goal of the talk here is to sort of try to link those in thinking about these sorts of landscapes. But then a weather event had its, sort of cause a nonlinearity in my travel plans and led to this switch of day. But I think it's still, one of the great things about CSDMS is we get these perspectives on the Earth's surface from seconds or even less than seconds to, time steps of potentially thousands of years and thinking about the evolution of entire mountain range. So I'm going to try to bridge those, thinking about these types of landscapes in this talk. So the motivation of this is thinking about what sets river profiles in tectonically active landscapes or steep landscapes, right? So we have a river profile elevation versus distance downstream. This is from a figure from Kellen from a few decades ago, right? And this is a consequence of the uplift from lifting the landscape up and the erosion of the river incising into those uplifting blocks. And what Kellen points out is that these landscapes, the relief structure of them is dominated by these river systems. So if we want to understand topography over these timescales, we really need to understand how these river systems work and how they evolve. And thinking about linking those timescales, it's been recognized for a while that, right, we have to think about discharge variability within these river systems. Every day, if you go to a river, there's not likely much geomorphic work happening, let alone bedrock erosion, right? The flow fluctuates over time, and so that's what I'm trying to illustrate over here, right? We got these photos from France. Let's see, do I have a pointer here, right? Showing this river at very different flood stages, and this is a figure from Dimitri Leg showing a PDF, or probability distribution of different mean daily discharges from Eastern Taiwan, and pointing out that you have the sort of dry phases, low probability, you have some sort of mean flow, and then you have this sort of tail of bigger and bigger events. And it's only when you get above certain discharges is when erosion starts happening in these sorts of river systems, and that creates a lot of interesting predictions for how climate and landscapes evolve over these sort of long time scales. Likewise, we've also been recognizing in the community that sediment matters a lot in controlling the evolution of these river systems. This is a picture from Taiwan on the left and Arizona on the right. The access for the river to do work on rock, it was very, very different in these two landscapes. And this has been, sort of looked at in lots of different perspectives with different modeling tools, with different sort of observations of thinking about what is the role of sediment in these channels in controlling their morphology and the evolution of these river systems over these long time scales. What I'm going to bring in today is thinking about sediment supply variability over time. So we've thought about this in different sort of landscapes, spatial perspective, but the sediment coming off hill slopes into river systems is quite stochastic over time, just like we saw, right, with water discharge, right? And we can see examples like this. Here's some photos of a river in the Catalina Mountains outside of Tucson following a big storm event, a monsoon in 2005. A Google Earth image from South Korea showing that these river systems and these sort of steep bedrock landscapes get these pulses of sediment that a grade a grade sediment and change the access of the river to eroding bedrock, right? So it brings up what is the consequence of the sediment supply variability over time on these fluvial systems, and thinking about this across timescales. So if we think about it on the short time scale, I'm gonna start with this picture. This is a Google Earth perspective looking, we're sort of hovering above the landscape, looking downstream this main channel. And the point I want to make is that, you know, the sediment supply variability is what leads to cascading hazards, right? And what I mean by cascading hazards is what happens on the top of hill slopes affects what happens on river systems. And as that sediment moves through the system, it can lead to various hazards, right? Landslides themselves, debris flow runout, and then also change the river system downstream, which is where my sort of interest and expertise comes in. So I'm sort of highlighting a little village here. I want you to notice it's quite far away from the river. Doesn't really have much sort of, you can't really see this in this photo, but it's 10 meters above, that terrace is at least 10 meters higher than the river system. Well, this is, I got this perspective view because it very much matches, or very closely matches, a view out of a helicopter following Typhoon Morakot in that same landscape after this very, very large typhoon in 2009 that I'm going to talk about in the following slides. But now we can see this little village that was far from the river now has along channel landslides. It's also now probably at risk of flooding because so much sediment has entered the river system and changed sort of the hazard outlook. So this sort of this cascade of sediment and the hazards that emerge, right, is sort of the core of this new NSF project that Irina mentioned in the introduction called CLASH. It's the Center for Land Surface Hazards. It's a new 5-year, $15 million initiative funded by NSF. I'm a co-PI. The PI is Marin Clark at University of Michigan, where the center is housed with a cooperative agreement with NSF. And we're trying to link our disciplines, both the geomorphologists and the engineers that study problems from the development of the critical zone, which weakens hill slopes, to the initiation of landslides, the run out of the sediment and debris flows, and then the impacts of all this sediment as it works its way through fluvial systems. So that's sort of the scientific motivation behind our center, is to understand that, observe it, model it, and do our sort of the science that we do as geomorphologists, but with this sort of framework of thinking about better understanding these cascading hazard systems. So I want to talk a little bit about or motivate the sort of landscape modeling with some observations from this Typhoon Morakot that happened in 2009. This is, you know, Taiwan's a kind of a landscape of extremes. This is an extreme of extremes. Look at this precipitation, total accumulated rainfall here. This is over 4 days, and there are rain gauges that measure 1.8 to 3 meters of rain. So that photo now, that gives you some perspective, like that was, you know, biblical type storm event that got unleashed on this landscape. In this image on the right, you can see all the landslides that were mapped as a consequence of that event. And the river systems had clearly a major impact. And so here's a couple photos from a river system right about here. This is a photo from 2003 that is on Google. You can sort of see this hill slope back here. Pretty sure that's this same hill slope. I visited this in 2009, and this is what the system looked like. Completely different as this landscape is responding to this one storm event, one weather event a decade before. So what we wanted to do is figure out how much sediment is in these river systems and how long is this, you know, this landscape is eroding at 3 to 4 millimeters per year, right? Like that is really, really fast geologically. How does it handle this when it's got to deal with all this sediment? So a former PhD student of mine, Clark Delisle, came up with this approach to just sort of, where you could just map out the banks of where this aggradation occurred and get a pre-event DEM and fit an envelope to sort of get at volumes of sediment stored in these river systems. So we did that, or Clark did that, I should say, along this entire transect of southern Taiwan from the south to the north, and was able to calculate sediment volume in these river systems. And we can see it varied by 3 orders of magnitude as you move north into the steeper and steeper landscapes that got hit by more and more landslides. So we were able to get a constraint on the amount of sediment that was delivered in this one event to these river systems. We then wanted to ask the question is, what is the legacy of this? How long is this river going to be responding to this pulse of sediment? And we don't really, we do this in a very simple way of just calculating bed load sediment transport rates, assuming a proportion of that sediment as bed load, and using 10 years of daily water discharge data from gauging stations. We can look at the percent of sediment removed as a function of distance north, so distance north from the southern tip, moving north into the steeper and steeper parts of the landscape that got more and more landslides due to Typhoon Morakot. And so what we can see is in the south, these river systems easily accommodated any landslides that occurred. They were able to evacuate that sediment, right? And they're not having access to bedrock kind of problems in terms of erosion. Whereas as we go into the north, we get into the parts of the landscape that are subject to a lot more intense landsliding. And these rivers have only removed 10% of that sediment volume, right? And this is ignoring extra sediment that may have been falling down after the event that continues to supply these channels. And so you do the inverse of that, you can actually get the estimated time scale of removal. If you can only remove 10% in 10 years, that means it's going to take a century to impact this, or it's going to be a century of impacts on this river system. To link this to hazards, I'm going to have a slide here of a recent master's thesis from my research group from Brooke Santos, is now a PhD student at University of Washington. She went and got pre and post Typhoon Morakot aerial photos. In Taiwan, they always fly them in stereo, and so we're able to create 3-dimensional models of the river before and after this typhoon. And so here's a photograph before and after. Sediment, still a lot of sediment before, even more sediment after. But then we can do a DEM of difference and see how this river system responded to this pulse of sediment. We see a lot of along channel sort of bank failure and landslides. You see a pretty decent sized landslide right here. And then in the main stem of the river, you can see quite a bit of aggradation, up to 17, tens of meters in some places, at the maximum of 17 that we observed. I think that was up here. We could take profiles. So this is a profile right through here. The black is the pre-Morakot cross-section. You can see that there was this little channel island here that got wiped out by Morakot. And then even into 2015, the sediment kept coming through the river system, continuing to aggregate it. So Brooke took these DEMs and ran them through HECRAS and was able to map out the inundation area, so the flooded area during different size discharge events. So we have different discharge events. The dashed line is the 100-year recurrence interval, right? And we can see that right after Morakot, we had a 20% increase in inundation area. As you get to the higher events, there wasn't that much change because we also widened, which accommodates some of those flood areas. But then as sediment continued to come down 6 years after and continued to aggrade, we continued to expand the inundation area for a given flood event. So that's sort of that link of thinking about our geomorphic processes and linking them to these sort of cascading hazards. But as I promised, I wanted to bring this back to thinking about landscapes and landscape evolution, and thinking about 2 very different landscapes: Taiwan that we have been talking about versus a place like central Indiana where I live, right? And thinking about the variability of sediment supply coming off these hill slopes to these river systems and what that means to the evolution of the rivers. The approach is to use this a model. It's called Otter. It was first published in 2018. So a typical river profile model, so your elevation versus distance downstream, right? You sort of have your pixels here, and then you assume a scaling with channel width and drainage area, and so your river gets wider and wider. But as we look at rivers around the world, we see channel width can evolve. If you've got, a steepened part, sometimes it'll narrow. Other places it'll widen in response to other forcings. And so I developed this model to sort of give us a 1D river profile model that can account for dynamic width changes. Things get really interesting in dynamic width when you start to include the effects of sediment. So we have an Exner equation and bed load transport model, so that the change, the topographic evolution is equal to the uplift minus the change in, or the Exner equation, essentially, when you're covered with sediment. When bedrock is exposed, we have a bedrock erosion model. And in this case, we're just going to take a very simple approach where the rate of erosion is equal to the shear stress times some erodibility of the rock times the fraction of bedrock that's exposed. And we use just the simple linear cover model from Leonard Sklar. It's just a ratio of the supply to transport capacity, supply from the reach upstream, and any additional area you have. What Clark did to accommodate this concept of temporally variable sediment fluxes is added in variable water discharge supply. So just like the Dimitri log sort of plot of variable PDFs, or a PDF of water discharge, but then also linking the supply coming off the hill slopes into the river to these weather events. We're not just trickling sediment in every time step at the same rate. It's related to how hard it rained on the landscape, essentially. This end factor just ensures that we maintain, mass balance, and we're not supplying sediment over the long term that's faster than the rate of rock uplift or less than the rate of rock uplift. So what does this model do? Well, of course, it predicts a river profile like any sort of river profile model does. We've seen zillions of those. But it's doing it with weather events, right? We have a 2-week time step in these particular model runs, right? And we're just changing water discharge over time. We're just plotting sort of the maximum from that given year. And so we can do this time series of water discharge, but we're also evolving the sediment supply with those weather events as well. And so we have these periods where we have sediment cover, then we remove that sediment cover, we start incising rock, and back and forth. And so you can see some really interesting dynamics of the river shifting or responding to individual weather events. And you can see sometimes those weather events leave a long legacy in which you've shut off access to the rock while this pulse of sediment is being moved to the landscape, and you're limiting erosion into bedrock during those time periods. So this is a way to sort of summarize that video. Here we have model time in years. This is after the system has reached its topographic steady state. So we run this for millions of years to reach a topographic steady state. And then we zoom in to see what's actually happening, how often erosion's happening versus sediment cover. And so we can look at individual weather events, and then we can see these pulses of sediment, right, that can last for decades, like we saw in Taiwan. And then we have periods where there's actually bedrock exposure, and we can have erosion rates happening. So the brown here is our magnitude of sediment cover, and the red is incision that is happening into rock. And so these are cases of high sediment supply. And so we have these long legacy effects of these big events. And so when there's most of the time you're not adding that much sediment from the hill slopes, and then you get a big event and you get a big slug, right? That's what I mean by high sediment supply variability. Whereas low sediment supply variability is, every year you're adding a little bit. Yeah, you have some big weather events that add a little bit more, but not out of proportion to essentially changes in transport capacity of the river system. So to link back to the cascading hazards sort of comment that I promised in the title slide, right? These periods, these red where we're actually incising, is like the pre-Morakot, where we had bedrock exposed, we're doing geomorphic work on rock rather than just moving sediment. Whereas these periods of these legacies of these single weather events are what we're seeing today, even a decade after, now a decade and a half after Morakot, and these rivers still sort of chock full of sediment. So we can look at this in levels of complexity. So this is just sort of looking at individual events and what they're doing on the landscape in terms of eroding rocks. This is a PDF of how frequently these different discharges happen in this model run. So this first one was we're not thinking about sediment transport or using Exner equation, but we still have a critical shear stress to start eroding rock, right? And as you get bigger and bigger events, you erode more and more. The colors here are mean event erosion and as a fraction of the total erosion done. So you need to overcome a threshold, and then as you get bigger and bigger events, you have to think about all of them in that context of understanding. As we add sediment, but if we do it with low sediment supply variability, so just a constant trickle, the first thing that you observe is that threshold goes to a lower discharge, and that's because we add sediment, we now have cover, and we end up with steeper channels. And so for to get the same shear stress, you could do it at a lower discharge, but with a slow sediment supply variability, we get that same general trend. A little bit less erosion during each event because of cover, but in general, the same sort of model behavior. When we think about steeper landscapes that have high sediment supply variability, like Taiwan, what happens is we end up with an upper threshold where certain discharge events bring in so much sediment, you overwhelm the system's transport capacity, grade, and end up with no bedrock erosion above certain size events. What that does is it pushes sort of the important events to lower sort of more moderate water discharges in terms of thinking about eroding bedrock and evolving these landscapes. So when we think about temporal variability of sediment supply, we end up with an upper threshold of incision due to the supply exceeding capacity. So we can sort of conceptualize this in this sort of quadrant of the number of events per magnitude and then the ratio of how big it is versus the mean event. The point of this slide is the upper two examples are high sediment supply variability, and we're mapping out the capacity versus the supply. And so the green here are events in which cause net aggradation, right? So these are these upper thresholds that stop erosion and leave a legacy in the landscape, right? They're like a dump truck arriving when the weather event comes and just overloading your river system. Versus systems like you might expect in southern Indiana, where the big events sweep the system clean of sediment and access bedrock erosion. So this kind of gives us a test, right? If you're wondering, is this landscape high sediment supply variability or low sediment supply variability, go out after a big event, what do the rivers look like? Are they net aggradational or do they get swept clean of bedrock? Taiwan, clearly net aggradational. There are, examples in Hurricane Helene, right, that just happened in western North Carolina, where there's pretty long stretches of rivers that have been swept clean of rock. Even though there was tons of landslides during that event, there weren't enough to overcome the enhanced sediment transport capacity during those events. So that might be an example of a landscape with a lower sediment supply variability. So I'll wrap up with just highlighting this point that I think we have to think about sediment supply variability and understanding river systems, obviously over different timescales and for different implications, from hazards to thinking about the evolution of these landscapes. And it really highlights, I think, a big research gap within our discipline is that we don't have models that link weather events of hill slope sediment supply to river systems. We can conceptualize them. We have landslide models and things like that, but I'm not sure that we're really capturing the essence of what controls the temporal variability of sediment transfer from the upland hill slopes into river systems. And I think that's going to be a big gap that we need to overcome to really understand linking these events from the event timescale up to landscape evolution. So with that, I'll leave you with the ground view of that river system where you can see multiple events like this in the past. Thanks.
We'll take one question for Brian. One question?
All right, Kellen.
Question I have for you, have you factored in how those biggest floods are less and less common, so that their integrated effect often dies off anyway.
Yeah.
Typically, the just past the threshold is the most important, because they move up and they happen relatively frequently. So, how much does this shift back?
Yeah, I mean, it's probabilistically based. So the biggest of events happen very infrequently, but when they occur, they do a lot of erosion. But you're right, in terms of you want to get to like a geomorphic effective event, it has the same effect of it pushes that geomorphic effective events to lower and lower discharges, essentially. You're right, it's just above threshold if you count the frequency. That gets into the variability of the water discharge parameter, and I didn't really get into that talk, but we explored that, and it has the effect of pushing it to lower discharges as well.